All right, starting a brand new chapter, stoichiometry applications, which is mostly review. Here's the explicitly review part. So stoichiometry, remember, is just converting between chemicals, essentially. So we can write out balanced chemical equations, balanced reactions. This shows us the number of each reactant relative to the other reactants and the products. So we could say that if we put in 3 moles of hydrogen, how many moles of nitrogen, or how much nitrogen do we need to react with that? So it'd be starting from the amount of hydrogen, 3 moles, going to the amount of nitrogen. It turns out 3H2, that's our hydrogen, reacts with 1N2. Our conversion factor is the ratio, the stoichiometric ratio. I usually just call it a ratio. So our conversion factor is that we would need 1 nitrogen for every 3 H2 that we have. And our solution map would look something like this, bottom line. Hopefully that's all review. Hopefully you are just sitting there nodding along. Yes, I get this. Yes, I know this. If, here's another one, if 2 moles of NH3 are produced, how much of each reactant was used? Typically for these problems, we just start with whatever we have numbers for. It's a common point of confusion that like the direction that we're working like really confuses some students. Just start with the numbers that you're given. So we're given 2 moles of NH3 and we're asked to find how much reactant. Don't worry about whether it's on the reactant side or the product side other than identifying what we need to find, which is our reactants, our H2, and our N2. So our 2 solution maps, our 2 things that we're trying to do is go from NH3, which we were given, to H2. We were also going from NH3, again what we were given, to N2, that's our other reactant. Our conversion factors are the ratio of the NH3 ammonia to the H2, and also the ratio between our NH3 and our N2. So just looking at the numbers that are in front, our coefficients, and pulling those out to make these conversion factors. We must have put in 3H2 to get out 1, that should be NH3, that's fun. Subscripts are hard sometimes, I guess. So to get out 1 NH3. And so our 2 solution maps would look something like this. That's what we would be writing down and then plugging into our calculator. Questions so far? 1 thumbs up, 1 yawn, and a lot of blank faces. Love it. There are also instances where we will have different amounts of our reactants. We're not always going to have a perfect exact amount, like everything's going to get perfectly used up. Even if we have that situation, it's likely that one of them won't get used up all the way for reasons. And in industrial applications or in like lab situations where you're making something, oftentimes the cost of the reactants is not the same. For example, 1 reactant, I'm just making numbers up, might be $10 a gallon. That's a lot of reactant if it's just us working in a lab. Like a whole gallon of chemical for $10, what a deal. Another reactant might be $1,000 a gram. So if we're doing a reaction between these 2 things, which one do we want to make sure that we're using up? Which one's more expensive? Which one's more important that we absolutely make sure that it's getting used up? The second one, right? We spent $1,000 a gram on that. We might only be using 1/10 of a gram or 1,000th of a gram or 100, small amount. But we want to make sure that we're getting our money's worth out of that $1,000 a gram. And so we would use maybe 10 times the amount of the other one because it's dirt cheap, right? It's $10 a gallon. We're not really concerned about wasting 10 cents. But if we don't use up all of this $1,000 a gram reactant, we might be wasting $100. We might be wasting $10. We could use the whole gallon of the other thing, and sure, we'd be wasting most of it, but we'd be getting our money's worth out of this $1,000 gram product. It's also entirely possible that one of them, even if they're relatively cheap, one of them is just a real pain to get out of the reaction mixture. If it's not used up, then when we get to the part where we have to purify our chemical, one of them's a real pain to get out. But if we can make sure that it gets used up, then we don't have to remove it. It's gone anyway. And so limiting reactant is valuable for those reasons. If we want to find a limiting reactant and a theoretical yield and a percent yield and things like that, we do calculations like this. We've covered this, right? We've talked about this? Perfect. So more review. Let's say that we want to find the limiting reactant. The limiting reactant, the one that gets used up first, and the theoretical yield. The yield from the limiting reactant. If we start with 1.9 moles titanium, 3.5 moles of chlorine. We're going to use our stoichiometry, our ratio of coefficients. We'll look and see how much of the products can we make from each reactant. The limiting reactant is the one that makes the smaller yield. That means that it runs out first. And the theoretical yield is that smaller yield. We can't make the bigger amount because our limiting reactant will run out. We just won't have enough to make it. So finding limiting reactant and theoretical yield, if we start with 1.9 moles of titanium, 3.5 moles of chlorine. So our product that we're looking for the theoretical yield is this titanium 4 chloride, TiCl4. So we're going to do two calculations. We're starting with 1.9 moles titanium and going to moles of TiCl4. We could also go to grams. It didn't ask for grams though, so we're going to do the easier one. Also, I don't want to go to grams. So we'll do that for both of our reactants. If we were asked to provide an answer in grams, you can still do it this way. You'll just pick your limiting reactant and your theoretical yield and then take that one number to grams. Or you can take both of them to grams. It doesn't really matter. I just like doing less work, and so I would do it this way, personally. All right, so our 1.9 moles titanium. What is our ratio of titanium to titanium 4 chloride? It's 1:1. So we get 1 titanium 4 chloride out for every 1 titanium that we put in. And there's an assumption that we're making here. The assumption is that we have enough of the other thing to actually do this. That assumption is not always true. And that's why we have to choose the smaller number. So we would get out 1.9 moles of titanium 4 chloride, assuming that we've got an abundance of chlorine gas. Our other ratio is 2:1. We have to put in 2 Cl2 to get out 1 TiCl4. So we've got a 1:2 ratio. We cut that number in half. And the amount of titanium 4 chloride that we can get out of this reaction is 1.75 moles. That's a smaller amount of moles of our product. So even though we have more of the chlorine, it can only produce 1.75 moles of our product, TiCl4. That means that Cl2 is our limiting reactant. And 1.75 moles of TiCl4 is our theoretical yield. That's the most that we could possibly make given the reactants that we have. And if everything goes perfectly, we'll even have a little bit of titanium left over. Questions? All right, one for you to try. Consider the following reaction. It's balanced. You know that it's balanced because there's coefficients in there already. If you begin with those amounts, what's the limiting reactant and what's the theoretical yield of sodium fluoride in moles? So you don't have to do any molar mass stuff. Let's give that a shot and I will take roll. All right, coming back after the pause. We are beginning with the two numbers that we were given. 2.4 moles of sodium, 1.3 moles of fluorine. And we want to find the limiting reactant and also the theoretical yield of sodium fluoride in moles. So starting with our 2.4 moles sodium, our ratio for sodium to sodium fluoride is 2 to 2. We'll get out 2 sodium fluorides for every 2 sodiums that we put in. You can optionally, if you want to, put moles in here as well. You would put moles on both of them. I don't put moles in there because the moles cancel out. So I'm just skipping that canceling out a thing. Being lazy again, as per usual. The 2's also cancel, and so we would end up being able to make 2.4 moles of sodium fluoride. From our other reactant, our 1.3 moles of fluorine, which is F2, our ratio is 1 to 2. We produce 2 sodium fluoride for every 1 fluorine gas that we put in. So that 2 to 1 ratio means that we could produce 2.6 moles of sodium fluoride given the amount of fluorine gas F2 that we have. To figure out which is the limiting reactant, we look at which number is smaller, the smaller number here being 2.4 moles of NaF, the top number. And so that is going to be our theoretical yield. And the reactant that went into this, into making this amount of sodium fluoride, was sodium, and so sodium is our limiting reactant. So sodium's the limiting reactant, 2.4 moles sodium fluoride is our theoretical yield. Questions? We can also expand this out, starting with grams, ending in grams. So just adding a step to each side. But the process for the stoichiometry part, that middle part, is the same. We're just adding that extra step of using molar mass on the front end and the back end. So let's say that we're starting with grams of sodium and grams of chlorine. We want to find, again, the limiting reactant and the theoretical yield. This time we're going to find it in grams. So the first thing that we would probably want to do, we could write out a solution map. If you're comfortable with doing these problems, you don't necessarily need to write out a solution map. It would be helpful for us to get our molar masses. If I'm remembering correctly, and my eyes are working properly, which they might be, sodium's 22.99. chlorine is 70.90, and sodium chloride, I'm not going to do that in my head, is 58.44. These all have units of grams per mole. So the number part goes with the grams, and that's per 1 mole. So starting with 53.2 grams of sodium, in order for this balanced equation to be helpful to us, in order to be able to do the stoichiometry step, we need to have these numbers not in grams, but in moles. Because they're different sized atoms, and so they have different masses. But if we're talking about the number of atoms or the number of molecules that we have, that's what's going into our chemical equation. So we'll take 53.2 grams Na, divide by our 22.99 grams per mole for sodium to convert it to moles. And then we can do our stoichiometry step. We get out 2 sodium chlorides for every 2 sodiums that we put in, so we've got a 2-to-2 ratio. Since we've got a 2 on the top and a 2 on the bottom, we don't need to put that into our calculator. So that's our stoichiometry step. And then we're going to bring it back to grams by multiplying by the molar mass of sodium chloride. So what we're putting into the calculator, 53.2 grams times 58.44 grams divided by 22.99 grams. You don't put the grams part in, but 53.2 times 58.44 divided by 22.99. You can do those in any order, by the way. So the yield that we could get from this reactant, somewhere in the range of 135 grams sodium chloride. Again, the assumption that we're making is that we would have plenty of our other reactant, or reactants, in this case just chlorine. That's not necessarily true, which is why we have to do a theoretical yield from the chlorine as well. Any questions so far? All right, so our 65.8 grams of Cl2, chlorine gas. Our molar mass for chlorine is 70.90. So divide by 70.90 grams per mole to get moles of chlorine gas. And now, since we're in moles, we can do the stoichiometry step, the ratio step. And our ratio here is 1 chlorine in, turns into 2 sodium chlorides out. So 2 NaCl on top, 1 Cl2 on the bottom. The Cl2s cancel out. And then we multiply by the 58.44 grams per mole to get back to grams for our sodium chloride. So we're putting in 65.8 divided by 70.90 times 2 times 58.44. And the number is 108.4 ... grams sodium chloride, which it turns out is the smaller amount. So this, rounded to 3 significant figures, would be our theoretical yield. And chlorine is the left, right. It's the limiting reactant. because it makes the smaller amount of product. When you're doing these problems, if you want to save yourself a step, something that you can do that's optional, if you notice, both of these have the same last step. They also have the same multiplying by the coefficient for the sodium chloride. If you want to leave that part off, since it's the same for both of them, you can figure out which one's your limiting reactant and then add those steps on after. That's optional. You don't have to do it. If that doesn't make sense to you, don't worry about it. It doesn't exist. But it's something you can do. That's what I do, or what I've done in the past, at least. All right. We're halfway through the slides, if you can believe it, for this chapter. So here's one for you to try, just to make sure that we've got our limiting reactant and theoretical yield down. I'll also give you the privilege, the fun, the experience of calculating your own molar masses. All right. Coming back after the break, after the pause. This is hopefully, you're looking at this problem and thinking, this is easy, this is no problem, no big deal. That's ideally how you should feel about doing this problem. If you're like, I have no clue where to start this problem, even though we just did an example, but like if you were coming back to these ideas and you're like, I've got no clue what's going on, that's not a great sign. It's not the end of the world, but like use that as a little bit of an indicator for yourself, like, hey, time to study up, because you are going to need to use these ideas, you are going to need to know these ideas for exam 4 and for the final exam. So keep that in mind. That being said, we've got some molar masses. This one's 17 point, I forget what the decimal part is. 0.31. Great, there's our molar masses. If you need help on any of the steps, anything in the class, just as a reminder, you can come to office hours, you can ask me about it. I'm more than happy to re-explain stuff. Don't worry about looking bad. I would rather you come to office hours and like have no clue what's going on than you show up to an exam and just like bomb an exam, right? Like it might feel a little uncomfortable to come to office hours and like be asking about things that we've already done. Don't worry about it. I don't think poorly of people who come to office hours. I think highly of people who come to office hours because you're helping me not be bored in office hours, which is awesome. Okay, so we're looking for the maximum amount of ammonia in grams that can be synthesized with these starting amounts. So one of our starting amounts, 25.2 grams of N2, our other amount, 8.42 grams of H2. We need to convert these to moles. So we can divide each of these by their respective molar masses. That'll turn grams into moles. And with moles, we can do ratio. So for our N2, our ratio of moles of nitrogen to our product, ammonia, NH3, our ratio is that we get 2 NH3 out for every 1 N2 that we put in. And then to figure out the grams part of it, we multiply by our molar mass for ammonia, 17.031 grams. And we'll get some number out for that. That number is 30.6 grams NH3, which is ammonia. For the hydrogen side of things, we converted to moles with our molar mass, and then we need to use our ratio. We get 2 ammonia out for every 3 H2 that we put in. So that'll convert our H2s. Now we've got moles of NH3 ammonia, and our molar mass for ammonia is still 17.031 grams per mole. The moles cancel. Put the numbers in the calculator. And the number is 47.4 grams, not H, NH3. Which of these is the maximum amount that we can make? It is the 30.6. This is our theoretical yield. That's the actual maximum amount that we can make. It's not the bigger of the two numbers. It's this 30.6 because our nitrogen will run out. We don't have enough nitrogen to make 47.4 grams of ammonia. The theoretical yield is the maximum amount we can make. And we had to go through the calculation for both of them because I, at least, cannot look at 25.2 grams and 8.42 grams and just immediately know that one is going to be able to make less than the other. Questions? Perfect. Lots of chemical reactions, this is the new stuff, involve heat, either absorbing heat or emitting heat. Chemical reactions that are exothermic, exo meaning outside of, exothermic outside of heat or producing heat, emitting heat, or endothermic inside. Chemical reactions can produce heat, exothermic, or they can absorb heat, endothermic. So we've got some vocabulary words. Exothermic, endothermic. What kind of skeleton do bugs have? An exoskeleton. What does that mean about their skeleton? Where is it? It's on the outside. Their crunchy bits are on the outside. Our crunchy bits, mostly on the inside, endoskeleton. But I don't think you would ever hear somebody call it that. So there's your word connection. Exothermic, heat outside, endothermic, heat inside. The amount, the quantity of that thermal energy that's emitted in the case of exothermic or absorbed in the case of endothermic can be quantified with a function called enthalpy. Enthalpy is basically just heat. So if you see enthalpy, you can just think heat. Conveniently, it's got the symbol H, which you can think in your brain, heat. Some people might get mad about calling it heat or thinking of it as heat, but it works. So enthalpy of reaction, specifically change in enthalpy, this triangle in the front, delta, change in enthalpy, and then the RXN here standing for reaction. This is the amount of thermal energy or heat that flows during a reaction. It can flow out, it can flow in. The constant pressure part here is not terribly important for our class. We're only going to be dealing with constant pressure situations, so you don't really have to worry about that. Exothermic and endothermic we can tell for a reaction based on the sign of the delta H. So the sign of our enthalpy of the reaction depends on the direction in or out that the thermal energy flows when the reaction occurs. Energy in, aka endothermic, is a positive delta H. Energy out, aka exothermic, equals a negative delta H. This is kind of like money on your bank statement. The dollar sign amounts that you see if you're looking at like credit card charges or debit card charges. If you've got a negative number, that means that you spent money, right? Money came out of your account. If you see a positive number or no negative sign, then that means that money went in. It's the same way for this, but instead of our bank account or credit card statement, we're talking about the system being the chemical reaction. So we either put money in, we made a deposit of energy, or we took money out. Here's some visual of that. So our system is the reaction. / chemicals. In an exothermic reaction, that's this right picture, energy is released from the system. The system loses thermal energy, gives it to the surroundings. In an endothermic reaction, energy is absorbed from the surroundings. And what that means for the surroundings is in an exothermic reaction, the surroundings get warmer. So like a fire would be an example of an exothermic reaction. You're doing a chemical reaction that produces heat. An endothermic reaction will make the surroundings get colder. It'll feel cold to the touch. That's because the system, the chemicals, are absorbing energy. Here's what this will look like. So our delta H is negative for exothermic reactions. So an example of an exothermic reaction is the combustion of natural gas. And this is a balanced chemical equation. So this is what it'll look like on an exam. This is what it would look like on a test, for example, or on a homework problem, perhaps. So we'll have our balanced chemical equation, and then we'll also have, to the right of that, a delta H RxN, and then some value. In this case, what this is telling us is that it's exothermic, and the amount of heat that's being released is 802.3 kilojoules, a relatively large amount. And this is secretly per mole equivalent, basically, of reactants, or reaction, let's say. So for 1 mole of CH4, or 2 moles, and or 2 moles of O2. It's really both, but usually for these problems we don't do a limiting reactant part. So there's a secret per mole bit on there. The way that I put these into calculations is I will use this delta H just like one of our other coefficients, just like a stoichiometry problem. So I would take, for example, 1 CH4, that would be on the bottom if we're calculating energy out, and then this negative 802 0.3 kilojoules on the top. So let's say that we've got 1.5 moles CH4. We're going to burn that with excess oxygen. The conversion that we would write, negative 802.3 kilojoules for 1 mole CH4. And this will give us the amount of heat that's released from burning 1.5 moles of CH3. We can also add a grams part to the front. So we could start with grams of CH4. I think the hardest part of these problems is figuring out how to do the stoichiometry part. It's not that complicated, in my opinion. That's what it would look like in practice. All right, looking also at endothermic reactions. This positive sign will often be omitted. So for an endothermic reaction, this is an example of one. Our delta H is positive, and that positive sign will often just be left off because usually positive numbers, we don't bother putting a plus in front of them. So the system, the chemicals, absorbs 182.6 kilojoules per mole equivalent of reactants. Meaning that if we have 1 mole of N2 and 1 mole of O2 and they react, it's going to absorb 182.6 kilojoules of energy. If it's 2 moles of N2 and 2 moles of O2, then it would be double that amount. It'd be 300 and whatever the number is, 365.2. The amount depends, the amount of heat depends on the amounts of reactants that actually react. Usually we're not doing a limiting reactant problem along with these. And we'll specify the delta H usually on the right side of the balanced equation, like we've seen in the 2 previous slides. And there's a whole paragraph there that you can read as well. All right, so for backyard barbecuing, more than likely you're using liquid petroleum gas, or liquid propane gas, sorry, not petroleum. Propane is C3H8, so this is propane. And it also reacts with oxygen. And, as you might expect, it's exothermic. That's kind of the point of grilling, is to make heat, put it into your food. So this is what you would be given, right? The balanced chemical equation and the delta H off to the side. When 1 mole of propane reacts with 5 moles of O2, it forms 3 moles of CO2 and 4 moles of H2O, and this amount of heat is released. So we can use ratios between any of these 5 quantities. Any 2 of those we can pick and make a ratio between them, which is what I was talking about on that first exothermic example. So just try to remember this delta H. We can use it just like with stoichiometry to put it into a ratio with any of these reactants or products. Let's look at an example. Ammonia reacts with oxygen according to this equation, and we've got the delta H off to the side. We want to calculate the heat in kilojoules associated with the complete reaction of 97.32 grams NH3. Complete reaction just means assume that we've got enough of everything else. You would have probably done that anyway. This is just to cover our bases for the actually people who might say, well, you didn't say that we had enough of the other thing. This is how we cover our bases. And then associated with, you just keep whatever sign you get on it. We're not saying that's the amount of energy that goes out or comes in. Just what's the heat from this grams of ammonia. So starting with grams, what can we do with grams? Turn it into moles. We don't want grams, we want moles. So for ammonia, 17.031 grams per mole, we saw that earlier. So divide by that to convert from grams to moles. And you might do this as an individual step on your calculator, and that's fine. So we've got 5.714 ... moles NH3. How do we turn that into heat in kilojoules? Yeah, we use our ratio. So we're constructing a ratio with our delta H and the coefficient that we have for our ammonia. So 5.714 ... to mean that there's other things behind it. Our ratio, negative 906 kilojoules over 4 NH3. Or 4 moles NH3, if we want to be, sorry, not if we want to be if we want to be particular about our units, it should be moles NH3. So that 5.7 and change times negative 906 divided by 4. The amount of heat is negative 1,294.2 ... kilojoules. So negative 1,294 might be the answer. It might instead be negative 1.29 times 10 to the 3 kilojoules. On a multiple choice exam, it's going to be one of those two. It won't be both. You'll have one option to choose from. Make sure that when you're putting negative numbers on your calculator, if you haven't put negative numbers in very much before, there's a separate button for negative. It's different than subtract. If you put subtract, your calculator will tell you that the correct answer is syntax error, and that's never the correct answer. Questions? All right, one for you to try. Sulfur dioxide, SO2, gas reacts with oxygen to form sulfur trioxide in an exothermic reaction according to the following thermochemical equation. We've got our balanced chemical equation. We've got our delta H. Calculate the enthalpy change that occurs when 58.0 grams of sulfur dioxide is reacted with excess oxygen. Excess oxygen just meaning we aren't limited by oxygen. We have an abundance. Give that a shot. All right, coming back from the pause, we are starting with 58.0 grams of sulfur dioxide, SO2. We'll need to figure out what the molar mass of SO2 is. Sulfur is 32.06. Oxygen, we've got two of them, they're 15.999 each. Add those together with their grams per mole, should be about 64. 64.058 is a good enough number to use. So we convert our grams of SO2 into moles of SO2 by dividing by our molar mass. And then we do the stoichiometry step, the ratio step. 2 SO2, or 2 moles of SO2, and negative 198 kilojoules. So negative 198 kilojoules goes on the top, and 2 moles SO2 goes on the bottom. And we plug these numbers in. 58 divided by 64.058 times negative 198. It's negative 179 kilojoules. Questions about stoichiometry or enthalpy? Sometimes, possibly in the homework, the absolute value of heat the positive value, the magnitude of the heat is requested, and words will be used to convey the sign of the heat, absorbed or given off. So if you get a positive and you were supposed to get a negative, you get a negative and you were supposed to get a positive. It's possibly just like a word play thing. If you're confused, feel free to ask. And that's all for Chapter 12.